Module 2, Advanced Maintenance Strategies, Reliability Engineering, and Emerging Trends. Introduction. Welcome back to the second and final module of the course on maintenance engineering. In Module 1, we examined the foundational concepts including maintenance definitions, objectives, classifications, and basic techniques. We also looked into preventive, corrective, and condition-based maintenance strategies along with planning and scheduling principles. In this module, we will delve deeper into more advanced maintenance strategies, explore the importance of reliability and safety, consider cost and performance optimization, and finally, investigate emerging trends and technologies shaping the future of maintenance engineering. Section 1, Reliability-Centered Maintenance, RCM. Reliability-Centered Maintenance, often abbreviated as RCM, is an advanced maintenance strategy that aims to ensure that systems continue to do what their users require in their present operating context. RCM focuses not merely on preventing failure but on understanding the impact of failures in terms of safety, operations, and economics. The process of implementing RCM begins with identifying all potential failure modes of equipment and understanding the consequences of each failure. These failures are then classified based on their severity and likelihood. Maintenance tasks are developed accordingly, either preventive, predictive, or redesign strategies, to mitigate these failures effectively. RCM requires detailed knowledge of both the technical systems involved and the environment in which they operate. By aligning maintenance tasks with the operational requirements of the equipment, RCM enables organizations to use their resources more efficiently while improving equipment reliability and performance. Section 2, Total Productive Maintenance, TPM. Total Productive Maintenance, TPM, is a holistic approach aimed at maximizing the productivity of equipment by involving all employees, from top management to shop floor operators. TPM focuses on proactive and preventive maintenance to improve the operational efficiency of equipment. There are 8 pillars of TPM, including autonomous maintenance. Operators take basic maintenance responsibilities such as cleaning and inspections. Planned maintenance, scheduled maintenance based on failure rates and historical data. Quality maintenance, preventing defects through root cause analysis. Focused improvement, team efforts to improve equipment performance. Early equipment management, designing reliability into equipment from the start. Education and training, equipping all personnel with the skills needed for maintenance. Safety, health, and environment, ensuring safe and healthy work environments. Administrative and office TPM, applying TPM principles to administrative functions. TPM aims to achieve zero breakdowns, zero defects, and zero accidents, ultimately contributing to higher efficiency and lower cost. Section 3, Reliability Engineering and System Availability. Reliability engineering plays a crucial role in maintenance by focusing on the probability that a system or component will perform its required functions without failure for a specified time period. Several key metrics are used in reliability engineering. Mean time between failures, MTBF, the average time between equipment failures. Mean time to repair, MTTR, the average time it takes to repair a failed component. Availability, the proportion of time that a system is operational and functional. These metrics help organizations plan maintenance strategies, allocate resources, and make decisions on equipment replacement or upgrading. Reliability engineering supports condition monitoring, root cause analysis, and failure mode analysis, all of which contribute to improved maintenance effectiveness. Section 4, Safety Considerations in Maintenance. Maintenance activities often involve risks such as exposure to high voltage, moving machinery, and hazardous substances. Therefore, safety is a core component of maintenance engineering. Key safety principles include risk assessment, identifying and evaluating risks associated with maintenance tasks. Locker tagout, LOTO, a procedure ensuring that machines are properly shut off and not able to start up again before maintenance is completed. Personal protective equipment, PPE, ensuring that maintenance workers are equipped with the right protective gear. Training and procedures, Workers must be trained on safety protocols and emergency procedures. Regulatory compliance, adherence to national and international safety standards and codes. Ensuring a culture of safety not only protects workers but also reduces downtime, liability, and maintenance cost. Section 5. Cost optimization and performance metrics. One of the key goals of maintenance engineering is to optimize the total cost of maintenance while ensuring system reliability and performance. There are three major cost categories to consider. Direct maintenance costs, labor, spare parts, tools, and equipment. Indirect cost, downtime, production loss, and opportunity cost. Capital cost, cost related to equipment replacement and upgrades. Balancing these costs involves analyzing performance metrics, such as maintenance cost per unit of output, overall equipment effectiveness, OE, downtime per month or quarter, maintenance backlog. Organizations must use key performance indicators, KPIs, to evaluate maintenance performance. By tracking these metrics, engineers can identify inefficiencies and optimize maintenance strategies for better results. Section 6. Computerized Maintenance Management Systems, CMMS. CMMS tools have transformed maintenance engineering by automating and streamlining various tasks. These software solutions allow engineers and managers to schedule, track, and document maintenance operations more efficiently. Key features of CMMS include work order management, automates creation, assignment, and tracking of maintenance tasks. Inventory control, tracks spare parts and materials. Preventive maintenance scheduling, ensures timely servicing of equipment. Reporting and analytics, generates reports on maintenance performance and cost. Asset management, provides a detailed database of equipment and maintenance history. The use of CMMS helps reduce downtime, increase productivity, and lower maintenance costs by providing accurate data for decision-making. Section 7. Lean Maintenance and Six Sigma in Maintenance. Lean maintenance applies lean manufacturing principles to eliminate waste and maximize value in maintenance processes. This includes reducing downtime, optimizing spare parts usage, and eliminating non-value-adding activities. Six Sigma, on the other hand, is a data-driven methodology aimed at improving process quality by identifying and eliminating causes of defects and variability. In maintenance, Six Sigma can help improve response times, reduce failure rates, and enhance predictive accuracy. By combining Lean and Six Sigma methodologies, maintenance engineering can achieve higher efficiency, better reliability, and greater cost-effectiveness. Section 8. Outsourcing and contract maintenance. Organizations often outsource certain maintenance activities to third-party contractors. This approach allows companies to focus on their core competencies while ensuring that maintenance is handled by experts. Benefits of outsourcing include access to specialized skills and technologies, reduction in training and recruitment cost, flexibility in scaling maintenance efforts, potential for cost savings through service level agreements, SLAs. However, outsourcing also comes with challenges such as loss of control, communication barriers, and dependency on external providers. It's crucial to manage contracts effectively and establish clear performance expectations. Section 9. Maintenance auditing and continuous improvement. Maintenance audits are systematic evaluations of maintenance practices, policies, and results. They help identify strengths, weaknesses, and opportunities for improvement. Audits focus on various aspects: compliance with maintenance schedules, equipment uptime and downtime records, spare parts inventory management, documentation and record-keeping practices, training and competency of maintenance staff. Continuous improvement involves using feedback from audits, metrics, and employee input to refine maintenance strategies. Tools such as root cause analysis, failure mode and effect analysis, FMEA, and Plan Do Check Act, PDCA, cycles are commonly used. Section 10. Emerging trends in maintenance engineering. Maintenance engineering is rapidly evolving with the introduction of new technologies and methodologies. Some of the most notable trends include predictive maintenance. PDM uses sensors and data analytics to forecast equipment failures. Internet of Things. IoT connects equipment to networks for real-time monitoring. Artificial intelligence. AI analyzes vast datasets to improve maintenance decisions. Augmented reality. AR assists technicians with real-time guidance during repairs. Sustainability, emphasizing energy-efficient and environmentally friendly maintenance practices. These innovations are transforming maintenance from a reactive function to a strategic enabler of productivity and business growth. Conclusion. In this second module, we have examined advanced concepts in maintenance engineering, focusing on strategies like reliability-centered maintenance, total productive maintenance, and lean maintenance. We explored the role of reliability, safety, cost optimization, and CMMS tools in enhancing maintenance performance. Furthermore, we looked at outsourcing practices, audit procedures, and emerging technologies that are reshaping the maintenance landscape. Together with Module 1, this course has provided a comprehensive understanding of both the fundamental and advanced aspects of maintenance engineering. As you continue your studies or enter professional practice, remember that maintenance is not just a support function but a strategic asset vital to the success of any operation.